So today I want to do a review of chapters 1, 2, and 3 for exam 1. I'm going to use the review document. If you have any, let me pull up let's see, where is it? Pull up the chat. Put it over here. Since I can't hear anybody, I'm going to have the chat open where I can see inputs from that. It's covering up some of my stuff, but that's all right. All right. So if you have any, while we're talking about these various highlighted problems from the review document, if something comes to mind that you want to cover, then interrupt me and I'll keep an eye on the chat so I can see if you have a specific need. Otherwise, I'm just going to go into the highlighted problems. The number of milligrams in 6.6 kilograms. All right, we're starting with 6.6 kilograms. The type of problem we're dealing with is unit conversion or dimensional analysis. And the analysis tells us that we're starting with kilograms and we're going to end with milligrams. So we need a conversion factor. If we know what the single conversion factor is for milligrams to kilograms, we can use it right here. But if we don't, we can chain them together. So that's what I'm going to do. So what's equal to kilograms? Well, 1,000 grams, right? That takes care of the kilograms. And then we can convert grams to milligrams. We have 1,000, excuse me, my mistake. We have 1,000 milligrams in a gram. Or we could say we have 1,000th of a gram is a milligram. Either way works. 10 to the third on top or 10 to the minus third on the bottom will give you the same answer. Now, that's the thinking part. We know that we're going to end up with milligrams. That's good. So now all we have to do is crunch numbers. And 10 to the third times 10 to the third is 10 to the sixth, right? 3 plus 3. So we know this is going to be our power of 10, and this is going to be our coefficient. Now, you look at your answers, and if you find that one in there, that's B, that's fine. If you run across a problem that has converted the answer to standard notation, then, and you don't find this one in there, just convert this one to standard notation, and it should be there. So if we were to do that, we need to move this decimal point to the right 6 places. Right? Let's see, 1, 2, 3, 4, 5, 6. All right, I did that. I put that decimal there as a placeholder. But we know this number only has 2 significant figures. So I can't put that decimal there. With that decimal, we're saying that it has 7 significant figures, but it doesn't. So we have to leave that decimal out. And that gives us only 2 significant figures. All right. Number 2. When you're working word problems, whether they're short answer or doing some calculations, or in addition, maybe multiple choice, you have to understand that word problems are designed to do one thing. They're designed to do several things, but one thing for sure, they're designed to confuse. They're set up so that if you don't know the material, the question will confuse you. If you do know the material, then there's enough information there, either in the problem or from additional external sources like periodic table, where you can draw on that information and solve the problem. One of the ways that these problems try to confuse you is they give you more information than you need. So you've got to know what the question is and then go looking for the information to solve it. So when this problem says water has a density of 1 gram per milliliter, which of these objects will float in water? You will need information about each one of those objects, which is given. So first of all, the question is, which of these objects will float in water? What condition are we talking about that will determine whether a substance floats or sinks in another substance? We compare the densities. Right? So what we want to find, an object that has a density less than 1. So here are your objects, right? And we're going to calculate the density of each one. Remember, the density is mass per unit volume. And since water density is given in grams per milliliter, we're going to calculate the density of these objects using the same units. And fortunately, the units that are given are grams and milliliters. So the first one is 50 grams per 69.4 milliliters. Okay, let's go ahead and put them all up here and then we'll talk about them. 60.9 grams per 54.7 milliliters. And then the last one is 100 grams and 40 milliliters. All right. Now, the next question I have is, to answer this problem, do we need to calculate the exact values for each one? And the answer is no. We just need to estimate the value, whether it's greater than, equal to, or less than 1 gram per milliliter. Right? So if we divide 50 by 69, that's going to be less than 1, is it not? That's less than 1 gram per milliliter. 60 divided by 54 is greater than 1. And 100 divided by 40 is also greater than 1. So which one of these is going to float? Only that one. All right, so you look for your answer. B is the answer. Only one will float. All right, number 3. Convert minus 12.2 degrees C into Fahrenheit. So we're starting with minus 12.2 degrees C, and we want to go to degrees Fahrenheit. Well, there's a formula for that, and it should be in useful information. The one I have memorized is F equals 9/5 C plus 32. And that's the one we're going to use because we're taking degrees C and converting it to Fahrenheit. So we have 9/5 minus 12.2. The sign is important. Plus 32. And if we work it out correctly, we should end up with 10.0 degrees Fahrenheit. Okay. You also want to always keep in the back of your mind, does this answer make sense? Minus 12 is 12 degrees centigrade below freezing, which in units of Fahrenheit would be what? Well, the ratio is about 2. It's 1.8 actually. So this would be that many degrees, about 22 maybe, 22 degrees below the freezing mark. And 22 from 32 is 10. So we're good. That's a way of estimating the answer. So we see, does it make sense? Number 7. All right, 232.0 degrees Fahrenheit is equivalent to, and all the answers are in degrees C. So we want to go from Fahrenheit, we want to go from 232 Fahrenheit to degrees C. And if we take the formula that I've memorized and solve it for degrees C, then the first thing we do is bring this 32 over here as a minus 32. And then we multiply both sides by 5/9. If we do that, right, 5/9, that cancels this one because 5/9 times 9/5 is 1. And then this one is 5/9 times this one is times everything inside that parentheses. And that gives us C. So now we can answer the problem by inserting 232 in here. Oops, not yet, minus 32. Okay, so this is going to be 200 times 5/9. 32 can be taken as an exact number because it's part of the formula. So it doesn't have an impact on the significant figures at this intermediate stage. I know the rules say that 32, that we should limit it to this position, but this is an exact number. So it doesn't impact this value. And then 5/9 times that would be, well, estimated to be about 100. Actually, should be more than 100, actually. So the closest one I see on that list is 111.1. If you multiply this one out, you should get 111.1 degrees C. All right, that's number 7. And coming up is 9. Which of the following describes a chemical property of gold? Remember, a chemical property could be a static description of the potential behavior of a substance. In other words, if we say wood will burn, we're not saying it is burning. We say it has the potential for burning. We're talking about a chemical change there because the identity of the wood is changing into something else. So in this case, gold, a chemical property of gold, very dense, that's a physical property. We're not saying anything about the identity changing. Gold is a soft metal, that's also physical. Gold is an inert, non-reactive metal. That's the key. That one says gold will not react chemically with anything else. Now we know it will, but the statement itself is a statement of chemical property. The others obviously are physical properties. We found the correct answer. We can move on. And scroll to number 12. In the sum, the number of significant figures is. So we got 54.34. And we're going to add to that 4566. The temptation, and I've seen it all too often from students, is they only remember the multiply divide rule. The answer would be, if we multiply these two together, the answer would have four significant figures, because both of the figures being multiplied have four significant figures. But this is an addition. That's a different set of rules. So don't make the mistake of applying the wrong rule to this operation. What we have to do is line up the decimals, then add everything up. Okay, let's see, 10, yes, 10, carry the one, it's another 10, carry the one, it's another 10. So we can keep both of these decimals. That means 5 significant figures. All right. And let me make another point. Multiple choice questions are often constructed with the potential errors that students might make. So if I use the wrong rule and think that there's supposed to be 4 significant figures, I'll answer B, because 4 is one of the choices. Right? The person that created that question understands that that's a potential mistake, and they put that answer in there as a way of weeding out those who know what they're talking about. But the answer is D. That's 5 significant figures. Number 15. Which of the following is an element? All right. You have to think about your definition of an element. An element cannot be reduced further or split or decomposed, whatever wording you want to use, by chemical means. We've taken it down to its simplest form. And we look at alcohol, that's a compound. Salt of any kind, and we talk about salts later. Chemical definition of salt is not the same as table salt. But in this case, it doesn't matter. Salt is a compound. Helium is an element. It cannot be reduced further by chemical means. Sugar is a compound. Vinegar is a mixture of acetic acid and water. 5% acetic acid in water is vinegar. So it's not only a compound involved, 2 compounds actually, acetic acid and water. It's a mixture. So our answer is C. That's the only element in that list. All right, number 18. How many liters are in 29-ounce bottle of pop? Okay, this is our starting point, 29 ounces. And we want to end up where? With liters. So I don't know of a single conversion factor that will go from ounces to liters. We could create one, of course, but that takes too much time, right? We're in the middle of a test now. We want to get it over with. So we're going to chain these conversions together. First thing we want to do is look at what the information that's given. We have a conversion of liters in quarts. So there's our conversion factor to get to liters, right? We would have it down here. That would be our last one. Liters. It's the last one before you get to the end. And we know that that ratio is 1.0567. There. Okay. Notice I'm working backwards. So for this one, that means that we had to cancel this one somehow. That means this conversion factor has to have quarts in the numerator because it's in the denominator here. So do we have a conversion factor for that? Yes, we do. 1 quart equals 32 fluid ounces. 32 ounces. Okay. Well, as luck would have it, ounces cancel ounces, quarts cancel quarts, and there we go. We ended up with liters. So that's our chain conversion. 29 divided by 32 divided by 1.0567 will give you liters. And if we do our calculations correctly, it should come out to 0.86. Now, that has the correct number of significant figures because we started with 2. And these are all multipliers, so it's the same rule to the end, 2 significant figures. I'll also make another point, if I haven't before. When you have a number like that, if you write it this way, it's wrong. That decimal must be bracketed by a 0. In my class, at least. Now, I've had students come through and tell me that their teachers in high school said that it's okay to say 0.86. You can say 0.86, but when you write it, it better have a 0 in front of it. That decimal, if it doesn't have a 0, I call those orphaned decimals. They don't have both parents, right? So technically, they still have a parent, but this is analogy. So always put a 0 in front of those decimals. It's a very practical reason, right? At least in this side of the ocean, we use a period for decimals. I think in England and lots of other places in the world, they use commas. And they probably use commas so that you won't get them confused with the period at the end of a sentence. But you can still get them confused with commas that are in the middle of the sentence. So even in either case, whether it's a period or a comma, you better put a 0 there so that you don't get it confused with a period at the end of the sentence or a comma in the middle of the sentence. Or if you don't want to think of it in those terms, just say, the instructor said you have to do it, so do it. Down to 20. Oops. There we go. 20. So we want to identify the homogeneous mixture of those that we can select, the available ones that we can select. In this case, stop and think, what's the question? Which is a homogeneous mixture? Work the problem backwards. Which ones of these are mixtures? If you don't have a mixture, then you can throw that one out. All right, it fails at the mixture level. Gasoline is a mixture, right? Primarily octane and usually ethanol, and then some other ingredients that the manufacturer claims will keep your carburetor and your engine clean. But it's a homogeneous mixture, a solution. Copper metal, that's not a mixture, throw it out. C, jar of jelly beans. That's a mixture of different colored beans. Pure water, nope, it's a compound, but it's not a mixture. It's a pure substance. And soil, take my word for it. Soil is a mixture. If you cut down through soil and look at if you dig a trench and you look at the soil from the side, you'll see differences. You'll see differences in color as you move down the profile. You'll see differences in texture, or you can grab a piece of it and feel it. It might feel gritty at one level and very slicky at the other level. That's an indication of particle size difference. So soil is a heterogeneous mixture. It's not homogeneous, but it is a mixture. Jelly beans, they're also heterogeneous. Look at any jar of jelly beans and you're going to see clumps of colors here and there. They're not uniform throughout. And gasoline is definitely a homogeneous mixture. Anywhere you sample gasoline in your tank, the tank of your car, you're going to find the same composition of octane, ethanol, and the other minor components. So A is the correct answer. Number 22. A graduated cylinder contains 20 milliliters of water. An irregularly shaped object is placed in the cylinder, and the water level rises to 31.2 milliliter mark. If the object has a mass of 80.4 grams, what is its density? There's the question. What is the density? You're going to have to calculate the density. So you need this formula, right? Mass divided by volume. And you look at the answers, the mass is in grams, the volume is in milliliters. You look back at your problem, the volume is in milliliters, good. The mass is in grams, good. So what you need to do is decide, what's the mass? Well, it's given to you, 80.4 grams. What's the volume of that object? Volume, 31.2, yeah, goes up to 31.2 milliliters. So why did the water increase in the measure? Because we put an object in it. That difference is the volume of that object. So you just subtract the two. 11.2 milliliters is the volume of the object. And if we do our calculation right, it ought to be in the neighborhood of 7.8 or something like that. 7.18. Okay, I'll go for that. 7.18 grams per milliliter. Three significant figures, 3, 3. We retain 3 here because the decimal put volume. Output volume. Looks like the microphone's working, but my speakers are still kaput. All right, well, let me see. I'm going to do this and reshare chat up. Yeah, the room's still connected. So let me reshare the document here. Okay. Yeah, there it is. All right, we're back. When I process the video, I'll just cut that out. Back to number 25. Let's see. I want to pull up. Let me get my chat up just in case. Okay, 25. So this problem requires that we convert degrees Fahrenheit to Kelvin. I don't have a formula that goes straight from degrees Fahrenheit to Kelvin. We could create one, just use a little algebra, but for now, we're just going to apply the two formulas that we do know. Right? If we want to go from to Kelvin, we have to go to centigrade first. Excuse me, force of habit, Celsius. So if this is our formula, and saying that I don't feel like solving this equation for C, I just want to put the numbers in and then solve the equation. So I can do that. We got 61.2 degrees Fahrenheit equals 9/5 C plus 32. So how would we solve that? Well, you got to get this 32 on the other side first. 61.2 minus 32 equals 9/5 C. Okay. And then we want to put this on the other side. So it's 5/9 times 61.2 minus 32 equals C. Okay. And then we would take the value here. Might as well calculate that. And get my. Sometimes I can do these in my head and sometimes I can't. So I'm not going to take a chance on it. 61.2 minus 32. And I got 29.2 times 5/9. And that's 16.2 degrees C. Then to get Kelvin, we just add 273 to it. Uh, 0, 8, 280. Now, technically, that would be, no, sorry, my mistake. That's 9, 8, 289. So we would, well, this is an exact number, so you can still keep the decimal. But look at your answers to see which one's the best. It says 289.4. All right, that's the closest one. C is the closest one. And I suspect that it's slightly different because a different value here was used. Say, I think it's 1/7. So that would round off to 4. It would be 37, then we round it off one place and it'd be 4. So that's why the discrepancy. They used more decimal places in the conversion factor than I normally do. But as usual, pick the best answer. All right, 26. Which of the following processes is a chemical change? Now we're actually talking about the description of a change of identity. So which one describes a change of identity? Dry ice sublimes when left on the demo table in the lecture. It's carbon dioxide in a solid form and it's carbon dioxide in a gas form. No change in identity. Light on a candle burns until a bell jar is placed over it for a period of time. We are describing a chemical change. The wax in that candle is first being converted to liquid. That's a physical change. and then it's being converted to a gas, and then it's combusted. That combustion process is a chemical change. So B is a good answer. What about the others? A few drops of red food color added to a beaker of hot water, the water immediately turns red. All you're doing is creating a mixture. The dye is still intact, water is still intact, no change of identity there. Liquid nitrogen dumped onto the floor vaporizes at room temperature. It's still nitrogen, just in different phases. None of the above processes are chemical. That doesn't work. No, that's one of those squirrely answers. We found the correct answer, B. That describes a chemical change. 30. This is a test of your knowledge of prefixes for a unit modification. Which metric prefix is used to designate 1/10? We've got the choices here. M, K, C, little m, and D. This is mega. This is times 10 to the 6th. Kilo times 10 to the 3rd. Centi times 1/100th. Milli times 1/1000th. And deci times 1/10th. There's your answer. All right. 36. Excuse me. The volume occupied by 41.9 grams of mercury is what? This is simply a rearrangement of this formula to answer the question, volume, right? It wants to know volume. So we need mass divided by density. Now the density is in units of grams per milliliter, 13.6. Right? And the mass is 41.9 grams. That should work, right? These grams, numerator, denominator. What about that milliliters? Where is it located? I say it this way. The denominator of the denominator is the numerator. When you have a value or a unit in the denominator, and it's also in the denominator, that's the same as the numerator. So this becomes milliliters out here. And if we divide correctly, let's see, that should be about high threes, right? Or mid threes, 3.08, that's closest. That looks okay. If we do the calculation correctly, it should be 3.08. And that's milliliters. Let's see, next, number 40. Let's see, how many significant figures are in this number? 0.0040090. So we have non-zero numbers in there, right? That's significant, that's significant. We have zeros in there of all three types, right? We have zeros to the left, bracketed zeros, and zeros to the right. So these are not significant. These are significant. How about that one? That one is significant because we have an explicit decimal right there. So that's 5 significant figures. All right. Number 41. The SI prefix that corresponds to a factor of 10 to the minus 2, we did that one earlier. 10 to the minus 2 is centi. A centimeter is 1/100th of a meter, right? Centimeters about that big. Stacks 100 of them side by side, and you get a meter. All right. Moving on. Let's skip a few. A lot of these are redundant, but you probably would you'd benefit from working them. 47. All right, the result of the following calculation is how many significant figures? All right, let's put this up on the board in a fashion that looks familiar. Let's see, we have 0.4333, 0.4333, and the units are joules per gram degree C. Joules per gram degree C. That. And then we're multiplying it by something else that has a subtraction operator. 0.12 degrees C minus 31.12 degrees C and times 412.1 grams. All right. Are you familiar with this acronym? And describes the order of operation. It's especially useful if we don't have any parentheses in here. If you don't have the parentheses, then you go to exponent, multiply, divide, add, subtract. So within the parentheses here, we can do this operation. Let's say minus 31.12, right? We've lined up the decimals. If I wrote those correctly. Yes, okay. So this is 0, 0, 2. And that's degrees C. Same units, degrees C. So we have 3 significant figures there. And we're going to multiply, what's the question? The result has how many significant figures? All right, we don't have to finish the calculation. We've taken this one into account. We have 4 there. We have 3 here, and we have 4 there. So the answer is going to be limited to 3. 3 significant figures in our answer. We don't have to calculate it out because we can answer the question without doing that and save a lot of time on a test. 48. Which is an example of a homogeneous mixture? We looked at one of these before. All right. All right, which one's mixtures? Soil or dust? Yeah, it's a mixture. Sodium chloride? No, it's a compound. Aluminum is an element. Vodka is a mixture. Oily water is a mixture. So we have 3 mixtures. Which one's homogeneous? Only the vodka is homogeneous, right? That's primarily water and ethanol with a few other things. But that's the only one that's homogeneous, is the vodka. Let's see, a lot of repetition here, so we're skipping these and we're moving on down to 68. A cubic centimeter is equivalent to what other metric volume unit, right? This is just remembering. A cubic centimeter is equal to 1 milliliter. $71. Let's see, the state of matter for an object that has a definite volume, so it's either a solid or a liquid, but not a definite shape. That's not a solid, has to be a liquid. That's your liquid. And notice there are a bunch of others in there that are meant to confuse, right? If we're talking about a state, elemental is not a state. Mixed is not a state. Solid, liquid, or gas, that's a state. And our answer is liquid. Let's see. Repetition. Oh, okay. We're going to use this figure of a beaker to answer question 84. You take 20 milliliters of water from a graduated cylinder and add it to a beaker of this water below. So we're taking, let's see, this beaker of water is at, looks like halfway between 10 and 20. All right, milliliters. And we're going to add into that 20 milliliters. Okay. What is the new volume of water in the beaker? Wait a minute. You take 20 milliliters of water from a graduated cylinder, add to the beaker. Okay. So which one should this be? Well, there are markings here for tens of milliliters. We estimate this one, right? Tens. We estimate halfway between. So 15 milliliters is all that we can do. This is a certain number. This is an uncertain digit. All right, so 15 is the best we can do. So 15 plus 20, we have to throw that one out, right? Because add rule says we're limited there. So 35 is the answer. Not 35.0, just 35. We're limited by the least accurate device. Let's see, 94. Okay, which of the following is only a physical change? Leaves turn colors in the fall. Well, that's a chemical change, right? Because you got decomposition of the leaf so that well, actually, technically, if we're only talking about the colors of the leaves, well, you have to know something about biochemistry. So let's hold A as possible physical change only. It's very likely there's some biochemical changes that create those colors. A banana ripens. When it ripens, it's undergoing chemical change. Cookies burn in the oven. Oh yeah, we're carbonizing some of that sugar. Sugar dissolves in coffee. That's a physical change. All you're doing is taking a solid, putting it into a mixture where it's in solution. At least two of the above exhibit only physical change. When it says only physical change, that's the kicker, only. For leaves turning colors in the fall, part of that is physical change and part of it is chemical change, I think. So that would be the disqualifier for A. It's not only a physical change. Let's see, 107. A blank is a summary of observed behavior, and a blank is an explanation of behavior. So when we're just summarizing what we observe, we're talking about a law, right? And when we're trying to explain why the behavior happens, we're talking about a theory. So B would be the best answer. The first blank is a law, second blank is a theory. $114. Your friend is 5 feet, 9.8 inches tall. What's your friend's height in meters? Well, we've got two problems here. 5 feet and 9.8 inches. 9.8 inches. Are we given conversion factors? No, we're not. You have to look them up. I think they should be. Let me check the useful information to be sure it's there. Let's see. Yeah. There's enough information in the useful information to allow you to solve this problem. So I would suggest converting everything to inches. The reason I would do that is because I know the conversion factor from inches to centimeters. So if we convert this 12 inches per foot, right? That would be 60 inches, wouldn't it? Like that. Because this is two significant figures, 60 is 2. All right. So now we add those together and we get 69.8 inches. Now here's the problem with rounding that off. We could introduce a rounding error, but I'm going to do it anyway because those are the rules. So if we round this off, that's 70 inches. Okay. Now we can convert to get to meters by going through centimeters. Right? And then we can go to centimeters to meters. All right, so if I do that, 70 times 2.54 divided by 100 is, let's see, that would be 1.8, 1.8 meters. Yeah, 1.8 meter. So this is an example where the problem is a little more complex. You have to break it into logical pieces. The logical first piece was this one, converting 5 feet to inches. And then we add them together, and then we could go and finish it off with a unit conversion. Actually, a second unit conversion. 116. Which of the following is an incorrect description? Okay, let's say we got A, B, C, D, and E. And let's see, are there any squirrely ones? No, they're all unique answers. So which ones do not compute? A homogeneous mixture. That's good. That's a solution. That's a perfect description of a solution. A solid element. Oh yeah. Solid element like gold. That works. A solution of gases. Oh yeah, we're breathing that every day. Mostly nitrogen, 78% nitrogen, 21% oxygen, and about 1% argon, and then trace amounts. A mixture of solids. Oh yeah. Example of that, brass. copper and nickel. And then E, a heterogeneous compound. Heterogeneous or homogeneous describes a mixture. A compound is a pure substance. So that one doesn't work. There's our answer. Let's see, scroll down to, oh, we're going to need this burette. Let me see. I need to reduce the size of that so we can get it all on the screen at the same time. That's good. That'll work. Okay. So 119. Yeah, using 0 as your reference point. What that means is the liquid in that burette was initially at 0. And notice burettes are calibrated from top to bottom. Graduated cylinders are from bottom to top. There's a reason for that. Graduated cylinders are calibrated to contain. In other words, you fill it up to a mark, and that's what's in the cylinder. So we go from 0 to 100, to 0 to 1,000, whatever the case may be. But a burette is calibrated to deliver. So we deliver from 0 in this case down to something past 20. So you have to read it the other direction. When you see 20, you're not going 19, 18, 17. You're going 20, 21, 22, 23. The opposite direction. So how much liquid has left the burette? Using the correct number of significant figures. So what we're looking at is, let's see how it's marked off. Between 20 and 30 are how many markings? There are 10 markings, right? So 1 mark below 20 is 21. 1 mark below 21 is 22. So let's see, it's kind of hard to see. Let me get a little closer. It looks like it's sitting right on 22. So if it's sitting on 22, and that is a marking, those are certain numbers. So we need to guess the last one. The last one we guess is that because it's not between 22 and 23, right? So we have 3 significant figures here. We have 2 certain and 1 uncertain, milliliters. So the answer for that one is D, 22.0 milliliters. Let's see here. 124. Aluminum has a density of 2.70 grams per cubic centimeter. Is that going to float or sink in water? It's going to sink, right? Ooh, let's see. I lost Amr. All right. So that doesn't answer the question, though. What is the mass of a rectangular block of aluminum measuring 11.1 centimeters by 22.2 centimeters by 34.5 centimeters, if the density is that value? So this is one of those complex problems that you have to break apart into pieces. We know the density equals mass divided by volume. And the question is, what is the mass? Right, so we're after this one. We want mass equals density times volume. We have the density right there, 2.70 grams per cubic centimeter. What's the volume? We have to calculate the volume. We're given the dimensions. We're given the dimensions of, let's see, it's like this, 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 and then this. Right? There's our block of aluminum. We got 34.5 centimeters on this one. We've got 22.2 on this one. And the height would be 11.1. So what's the volume of that thing? The volume of it is 22.2 times 11.1 times 34.5 cubic centimeters. And the density was given as 2.70 grams per cubic centimeter. So the cubic centimeters are going to cancel and give us grams. Right? And if we do our calculations correctly, we should end up with, it's in kilograms. Okay, we're going to have to calculate it. So the mass in grams is 2.70, 22.2 times that, 11.1 times, and 34.5 times. That's 2.295 times 10 to the fourth grams. Or, let's see, we have three significant figures. We can round it off to 2.3 times 10 to the fourth grams. Okay, you can convert grams to kilograms in a couple of different ways. You can use the conversion factor, 1,000 grams per kilogram, right? So this 3 subtracted from that one gives you 2.3 times 10 to the first kilograms. Grams cancel, leaves you kilograms. That's good enough. That's good. And the answer is in standard notation. So we move the decimal over to take advantage of that one, and we have 23 kilograms. Wait a minute. 1, 2, 3, 1, 2, 3, 1, 2, 3. Oh, this should be 3, 0. Yeah, 3, 0. Three significant figures. And this would be 23.0 kilograms. All right. 132. Convert degrees C to Fahrenheit. All right, we've done one like this before. I'm not sure. I don't know why I put this one in here because we've already done this type of problem. If you calculate it correctly using the formula, you should end up with minus 54.2 degrees Fahrenheit. Maybe the objective I was getting at here is watch the signs on your values, right? You don't want to say positive 54.2. In fact, well, let the formula do the talking. Right? You put the negative values in, calculate it. If a negative value comes out, there's your answer. 133. Which of the following involves no chemical change? Which means if it's a change, it's a physical change. Baking a cake, that's definitely a chemical change. Boiling water, that's a physical change. No change in identity there. Light a match, chemical change. Burn paper, drive a car, all those involve chemical changes, except for boiling water. 134. Copper has a density of 8.96 grams per cubic centimeter. If a cylinder of copper weighing 34.94 grams is dropped into a graduated cylinder containing 20 milliliters of water, what will be the new level of water? So we've got a graduated cylinder, and it's starting off at 20 milliliters. Let's just say that's 20 milliliters. And we're going to drop a piece of copper into this one, and we got the mass and we got the density, so we can calculate the volume. Density equals mass by volume, so volume is going to be mass divided by density. So the mass is 34.94 grams, and the density is 8.96 grams per cubic centimeter. So what's the volume of that piece of copper? 34.94 divided by 8.96 is 3.89955. Four significant figures, right? So we go here, and that means we're 3.900, correct? Right? That rounds up, one carry the one, and then carry the one. So this is cubic centimeters. All right, 3.900 cubic centimeters, which is equivalent to milliliters. Okay, so if we add 3.900 milliliters to this one, right? 3.900 milliliters to that one, our new level of water should be 23.9 because we have to chop it off right here. 23.9. That's D. Actually, that's not correct. Oh, it is. I'm sorry. There was an extra zero there. All right, so we do have 23.90. That's my mistake. All right, who's next? 137. How many significant figures are in the number? This is a scientific notation, and to determine the significant figures, you only need to look at the coefficient. So what we have here is two types of zeros. We have the bracketed zeros and we have the zeros to the right, and there's a decimal point. So all of those zeros are significant. We have 6 significant figures in this number. $138, is it? Yes. Which of the following is not a step in the scientific method? All right. What do we usually start off with the scientific method? An observation. Then we go to a hypothesis. We brainstorm or spitball, intelligent spitballing. We try to take the observation and make sense of it. And then we experiment. And we compare the results of the experiment to our hypothesis to determine if it was true or false. Not right or wrong, just true or false. All right, so how about this? Which of the following is not a step? Change results to agree with your hypothesis. Okay. Unfortunately, there are some scientists who have done that. And when they get caught, their career as scientists is over. Develop a theory or a model. That's possible. Perform an experiment, yes. Make an observation, formulate a hypothesis. B through E, those are all valid steps in a scientific method. Changing your results to agree with your hypothesis, that's known as fraud. Right. And we have a very notable example of fraud is I can't remember the scientist's name right now. First name is Michael. Is it Myers? I think. Anyway, he was the one responsible for the famous hockey stick. So a temperature here, degrees C, and he had time here in years before present. Right? And he said, okay, we're going along thousands of years, like 5,000 years before present, 4,000 years. And then he comes up to modern times, right? To zero, present day. And he says, here's what happens. He says, we're just nicely trucking along here. And then all of a sudden, when man starts spewing carbon dioxide into the atmosphere, this is what happens. Like that. That's the hockey stick. The fraud, the part that he changed, actually didn't just change it, he threw some values out. There was a little ice age, right? Along about in here, which would have dipped down. And then over here is the medieval warm period that would have destroyed his argument. So he just threw them out. Now, I think there are some institutions that are still giving him money to spew his nonsense. But as far as the scientific community is concerned, those who are actually thinking human beings, he's done. He has no credibility. Okay, back to the topic. 148. An example of a mixture is gold. The air, yes, the air is a mixture. Purified water is pure. Hydrogen fluoride is a compound, but it's pure. Gold is pure. The only mixture in that group is air. 149. How many of the following are compounds? What do we need to determine a compound? When you see the formula written, you've got two or more different elements. Water, dinitrogen tetroxide, sodium hydroxide, manganese dioxide, well, actually it's manganese 4 oxide, and hydrogen fluoride. Those are all compounds. So we have 5 compounds represented there. 150. How many of the following are pure compounds? Well, let's see. Sodium's not a compound. Oxygen's not a compound. Iron is not a compound. Sugar is a compound. Air is a mixture. Right? So the only one that is a pure compound is sugar. And that means the answer is B. 154. Helium is an example of what? Well, it's an element, right? It's not a mixture, and it's not a compound, right? So it has to be an element. 156, which of the following is an element? Well, let's see. What are our choices? Water, earth, salt, brass, oxygen. Oxygen's an element. Brass is a mixture. Salt is a compound. Earth is a mixture, right? Very complex mixture. Water is a pure compound. So the only element there is oxygen. 161. What is the result of the following multiplication expressed in scientific notation to the correct number of significant figures? All right, 5.46 times 10 to the third. And we're only talking about numbers here. 8 times 10 to the minus 3. 8, 0, 0. No, just 8, 0. Times 10 to the minus 3, correct? Okay, So 10 to the minus 3 times 10 to the 3 cancels those out. So we only have to be concerned with these two, right? So let's see. 0, 8 is 48. 4 and 32 is 36. 3 and 40 is 43. So we have 1, 2, 3 decimals. And how many can we keep? We can only keep 2, actually, because of this. So it's 40, 44. Or 4.4, let's see. 4.4 times 10 to the first. There you go. That C is the same thing as 44. 169. Get rid of the ghost. There we go. 169. A blank change involves a change in the fundamental components of the substance. A given substance changes into a different substance or substances. That's a description of a chemical change by definition. Oh, that's it? I thought I had more. I guess I don't. Oh, okay. Yeah, that covers everything that we've done in chapters 1 through 3. Okay. And we're finished before the end of the class. All right. If you're viewing this video and you have any questions, you know where to find me. Or if I'm not available and you can't find me, you can always go to Barry Pine, who is is a tutor for the physical sciences and math. And his information is in Brightspace. Actually, it's on the landing page for the course. Okay, we're done for today.